So hello, my name is Anthony Scopatz, and so I'm going to be talking to you today about reproducibility, and this talk is sort of a cross between Demolition Man and Quest for Fire in terms of this topic here. So I'm a postdoc at the University of Chicago, as John said. So what's like the one thing that we as computational scientists do pretty poorly, I would argue? Anyone? I mean, you got it from the title, right? So it's reproducibility. But, so the goals of this talk, in fact, are to show that in at least one specific instance, we can attain total reproducibility with a large-scale computational science code. Also to show that this isn't particularly hard in Python, and I have code that demonstrates this. And hopefully to inspire you to take some of these methods back to your home codes and then reuse these there. So on the boot heels of what Fernando is saying and such, maybe version control gets you 80% of the way there, but this talk is really about that extra 20% and bridging that gap. So a little bit of soapboxing to start off with. Much of what we call scientific computing, I would argue, is sort of computing about science. It's computations around scientific problems, but isn't the science itself. And this is one of Greg Wilson's main points, is that sort of applying the scientific method to computational science processes itself is actually kind of a hard problem. So this paradigm is something that I'm wanting to term peri-scientific computing, or computing about science. Sort of computing about science, right? And I would like to get us to a state where we're talking in terms of dia-computational science, where this is really computing throughout science. Computing is the substrate on which all science lives, and at that point we've sort of won. We have the ecosystem, and all scientists have to know basic computational mechanisms and follow best practices, whatever those might end up being. So the code that I currently work on is this Flash code. It's a big, multi-physics code. It's written in a handful of languages. It has these features. It's uniform grid, AMR. It's a big magnetohydrodynamics multi-physics code, right? So multi-materials, we now have this laser ray trace package for doing not just astrophysical simulations, but the thing that I do, which is high energy density physics and nuclear burning in stars and such. And specifically what I do is I model lasers shooting things and then burning through. So here's an example of a plot that I made with YT and matplotlib of there's a laser coming in from the bottom and it hits this thin slab, and we're plotting this jet that comes out, the electron number density of that jet. So, okay, so that's kind of what Flash is in 2 slides. Its architecture is kind of interesting in that we compile simulation-specific binaries. So that means that the source code has to be around at all points, which is very similar to Python. Even though it is in this mix of Fortran, C, C++, and a smattering of Python here and there. And it has this object-oriented inheritance model that is based off of POSIX directories, which is strange, but critical here. So to execute a Flash simulation, you have effectively 3 steps. There's a setup step, which is written in pure Python, where you figure out what simulation you're going to run and grab all the source code for that into a single directory. Then there's a build step where you actually build that code, that restricted subset of the code, to get a simulation-specific binary. And then finally, you execute that binary. Okay. So all of this used to be done by hand, right? Or it is done by hand in the shell. When I got there, I can tell you the atrocities that were committed against Guido and others in this build system, but that I spent a lot of time rewriting. But I also, when I was doing this process, I wanted to build a workflow management tool around these 3 steps and expand it. and have it be very modular. So with this goal of total reproducibility. So flmake has these 3 commands. It has a lot of others. But it also adds this reproduce command, which, because you are using this other system to run these things, you can capture the full environment for some value of the full environment at the time that you run these steps. And then, yeah, so, okay. And you can use these strategies elsewhere as well, as I mentioned previously. Okay, so the abstractions that we needed to make to have flmake work, in fact, was that basically, initially without flmake, the project directory and the source code directory were the same thing. So the source, if you wanted to make any changes to the source code for your specific application or simulation campaign, they wouldn't exist in a version control system that was independent from the mainline repository, and this is extremely annoying. So while that's sort of sufficient for one-off runs or something, it really doesn't capture all changes that you made for your specific simulations. And it made version control very difficult, as I said. So flmake adds in this capability where you can separate these things out and treat them independently. The other abstraction we made was that we have these description sidecar files, and these act as a version controllable way to represent everything that you've ever run. You know, they're just a JSON file that sits next to the simulation in the simulation directory. And this contains the environment, as I mentioned, version control information, which is basically just a shortcut for diffing. It also contains local source code modifications in the form of diffs and patches that, that it applies later. All of the run control information is stored in there as well. And of course, binary modification times. So in case someone has gone in there and interjected, you can detect that and say, aha, you can't this run is no longer reproducible. And this is sort of what they look like, right? It's just a sort of normal JSON file setup. Okay, and then that env down there is exactly just what you get out of os.environ. So, okay, that said, here's what the reproduce command does. It basically takes those description files and for every setup, build, and run command, will re-execute those subject to the following limitations. The project and source directory must be version controlled. That's your 80%. You can only depend on the things that it's storing, right? So if a run control file is not checked into version control, obviously it won't work, or it won't be reproducible. And then finally, you can't modify the binary that between stages when you originally ran your simulation. And here's kind of the workflow. So you pick each of these 3 commands that you want to do. You recheck out the repository for both the Flash source code and your project, and then you rewrite all the input control files, do some munging on the back end to make sure that the soft links are correct, and finally re-execute. You re-execute the historical command, which I'll get to in a couple moments here. Yeah, and then to do this, there were 2 other key features that you needed for the reproduce command. So the first one is meta version control, and I thought this was going to be much more difficult than it is. It ends up being about 225 lines of Python or so, and it's quite easy to just abstract everything that you need for version control system. So what you need is some way of getting info, right, the state of the current repository. The inverse operation of that, which is to check out or clone at that point. You need the ability to diff, and you also need the ability to patch. Relatively easy. And what we support, this is done for Git Mercurial Subversion and this release system. So in the event that you don't have a version controlled directory, but you have some release checkout tarball that you know about, you can just diff between that release and the normal version of the code, and that counts as sort of your most primitive version of version control. So even if your simulation scientist doesn't care to learn any of these systems, you can kind of sneak reproducibility in on them. Okay. And then there's this command time machine. This is executing the historical commands, right? So you have previous versions of flmake stored in your repository. You don't necessarily be wanting to run the current versions of run, setup, and build. You want to be running the version that was executed originally. And so this is done with some kind of neat namespace hacks. I mean, and it's sort of akin to this bootstrapping problem in kernels or compilers, right? So yeah, there's namespace sleight of hand, and relative imports is the other key feature here. Basically what you do is you rename the directory that you checked out to some other name, not flmake, as the top level namespace. Change it. Unfortunately, we changed that to just Python. And then you go into sys.path, add that at the front of your path, and then anything with the top level name Python at the beginning gets swapped in or swapped out of sys.modules at every one of these commands. So you're actually re-executing the original setup, run, and build that you had. So that's kind of clever. And here's I'm going to attempt to show you this, if you bear with me here. Is that big enough, I think? So I'm going to log into the code version, or this is running on our machine back at Chicago. Yeah, so you can see here this is a file that's already been run. There's these description files, they're JSON. We're just going to go ahead and clean these out in a full and complete way. And you can see sort of what's left, or simulation directory, etc. And then reproduce using the previous version, and you see it's checking out the original version of the command, resetting up. Now it's recompiling everything from scratch. This might take a moment or two, but then after this executes, it'll also rerun the original version that was stored in this JSON file. And you can just keep that JSON file around, and presumably when you go to publish your paper, you have everything you could ever need to reproduce that run. So maybe we'll come back to this in a moment. I'm just going to end on this note on replication. This is, Fernando mentioned previously to this, Titus Brown has this Amazon service that he provides. And in fact, there's a strong argument to be made that that's not reproducibility in a true sense, that's replication, because the entire environment is encapsulated, right? You have the same version of the compiler, you have the same version of NumPy, absolutely everything is the same. You're in the entire stack. You're not really changing anything and getting back the quantitatively same result. And so here's sort of a more formal definition. It's when you do the same thing with all the same data and same tools, and you get back the same thing. If you don't have that, you don't have sort of a scientific result at all, but it's not necessarily reproducibility either. But the boundary between these two things is actually fuzzy, as Titus and I sort of discussed in the comments of one of his original blog posts on this. And while the environment is stored in flmake, the flmake reproduce command doesn't try to reinstantiate any of these things. It just keeps it around for posterity. So for that reason, I kind of argue that the reproduce command is in fact reproducibility and not just replication. That might be a sort of subtle point made better in the paper. So let's see, did this finish? Aha, and it did. And we went and we ran through the entire simulation from that JSON file. And with that, I will take any questions you might have. So. Okay. All right. Thanks. Oh.
So it seems to me that your continuum between replication and reproducibility is the first two pieces of a three-step process, and this third step is broken. And the concern kind of arises when I put on my system administrator's hat, and I think about the environment you're running in, and I noticed when you were running your build, it had a particular version of the MPitch, MPI F90 that it was running. How much does the environment matter? How brittle are you with respect to changes in operating systems and changes in time? How long can you stay reproducible? The obvious advantage of replication, of course, is that it evades these problems, or at least evades them for longer. Do you have thoughts about that?
Yeah, so it is a continuum, or it's at least discrete according to the number of environmental variables that you have, right? And that's some huge combinatorial space, so it's effectively a continuum. Now, how brittle it is depends on the underlying code engine that you're using. I mean, here, Flash, it's tested on a wide variety of systems, so in theory, it should not be that brittle. And we've been running Flash for 13 years or something, so the reproducibility lifespan of Flash is probably pretty long, but if I was to do this for, say, some other code base that I have, which doesn't have that history and hasn't been as well tested on different platforms, obviously it's going to be more brittle, but at least you would have a record of exactly what you did the first time. Which is better than what most of us have now.
Right. Okay, thanks.
Yeah.
Perhaps you could say a little bit more about what you call dia computing and I call penthantic. Perhaps toward the development of elaborate formalism to apply scientific method and formalize it in a way that would be useful for these purposes. I think the language here is a problem, right? We kind of have these terms to talk about science in general, and there's been a lot of work done there over the past 400 years, but in terms of what we mean by reproducibility in computing is less well defined, obviously. And I think what we mean by things like testing and verification and validation in computing is a well-defined problem, and there are nice solutions there, but reproducibility is a space where there's still a lot of effort. So I think we need a language with which to talk about this.
Yeah, this is a great result. It's very interesting and something that's definitely needed. What are your comments about? So are you presenting your code with a paper, say that you publish your results in? Are you also publishing the flmake, making that available? How do you link the reproducibility to your published results? Is that stored with the publication? And also at the same time, how realistic is your estimate? At the beginning you said that just initially achieving your result was 80% of the way, and that you can add this rock solid reproducibility with another 20% effort. Do you think that's broadly scalable across the publishing world?
Yeah. So to answer your first question, I think it's actually very easy. You just stick this JSON file in your supporting documents or your supporting material part of your paper, and that's it. To answer your second question, the real purpose of this talk, in fact, was I thought this was going to be much more difficult than it ended up being when I set out. And I have the code that you can go and grab for a lot of these components that I highlighted. So, if you want this meta version control thing, it's, 13 or 14 functions in Python. I will just hand them to you. It's your job to integrate that. But it's also, building a workflow framework is also not terribly difficult, especially if you have an example. And ours is very modular, and you can look at that for inspiration. So the purpose here, in some sense, is to inspire you to steal my code and steal these ideas and take them back home with you. So.
Okay, let's take one more question, and then we'll break for the posters.
Okay, well, first of all, I want to commend you, because I think it did, especially in all the sciences that call themselves sciences, that are not real sciences, like computer science, material science, and so on. It has been a problem with the reproducibility, and actually, of course, it is still in the other hardcore sciences and medical technology also. So I commend anybody who tries to make an effort. And I think, you know, if you ever try to read a paper and a lot of people end up, and a lot, especially grad students, end up quoting things from scratch. And they don't know whether you know, even a call to an FFT, was it a, you know, a handwritten one, or was it a, you know, one that was actually using FFTW? And you don't really know what the results are and what they mean. And so I commend any tools for that. But I still think there's a way to go to get there. But I mean, we can discuss some ideas offhand. I know we're at the break now for posters.
Yep.
But I, first of all, wanted to commend you for what you did, because I think it is an issue in sciences in general, but also in the sciences that call themselves sciences, like computer science and others.
Right.
We have a very tough sell when it comes to, are the codes you're writing useful to other people, right?
Yeah. I'm not
beyond
gonna,
the paper, beyond the paper.
I'm not going to argue that this was a hard sell. I had to do this sort of under the covers at night on my own time, away from the prying eyes of my PI, right? So, yeah, it's not easy. We can talk afterwards during the poster. Yeah, find me during the poster session. So.
Thank you, Anthony, and take a break.